Thank you, thank you. Hi, everyone. Thanks for joining this session. Today, I'm going to talk about ransomware, and more specifically, we are going to focus on the data encryption stage that today is what makes things worse for companies. A little bit about me. I'm Antonio Cocomazzi, and I'm a threat intelligence researcher at SentinelOne, and I mainly deal with malware analysis and reverse engineering. And my main focus are cybercrime-related threats, like banking trojans and ransomware. Also, in my free time, I code offensive tools, and also I like to dip into Windows internals. In fact, you can see on the right my GitHub channel, in which I often publish offensive tools. And I have also previously presented at some international conferences like Blue Hat, Black Hat, and so on. What has been the main motivation of my research? The main motivation is because the data encryption today is the core functionality of every ransomware, and it's the means that enables their successful operation of extorting money. And what we can see today is that these kind of threats are still detected with static indicators, and static indicators, it's what is used for every threats, for generic threats. So for ransomware that are a little bit or more complex threats, we need something more. For example, behavioral indicators. But what is the problem? The problem is that extracting behavioral indicators from these threats means deep knowledge of these threats. And so lots of study, and it's very time intensive. So what was the goal of my research is to provide something that should ease the extraction of behavioral indicators. And the behavioral characterization should be, and we will see in the next slides, how this can ease this kind of extraction. And the final goal and the main results of this research that I will show is that identifying behavioral commonalities can provide detection opportunities that are generic enough to identify all of the most ransomware families, instead of relying, for example, on a specific behavior for a specific family. This is the agenda. There are the first three chapters that was a bit of a propedeutic work for my research. And then there is a more juicy part in which I will show the behavioral detection based on the overlapping implementation, in which I will show how ransomware can be detected generically. And then I will leave you with some final thoughts. Okay, the first stage of my research was to define the scope. As I told you, the scope was the data encryption stage. So I was not focusing on the entire kill chain of the attack of the ransomware, but I was focusing only on the locker payload, so the one that is disrupting the system. And the problem that I had at the time is that the threat models that were available at the time, like the MITRE model, was not wide and generic enough to categorize the ransomware behavior. So I had to find something else. And what I have found out is that the data encryption stage can be seen as 4 macro features, like, let's say, sub-operation performed by the data encryption. And what they are file and directories enumeration, file encryption, encryption parallelization, and encryption optimization. And then I had to select what are the ransomware families that we were interested in to look into. And I have selected which one, Babuk, Black Matter, Conti, and Rivol, that at the time of my research were the most dangerous ransomware that was around. Okay, some months later, what I have been doing for some months, I have been reverse engineering all of these samples, and it required a lot of time. And in this presentation, I have packed my very long research in a 45 minutes presentation, so I'm not going to present you every specific detail for every specific family. Instead, what I'm going to do is to provide you an intelligence, more insights from an intelligence perspective. So I'm going to highlight what are the main evolution, the main trends, and the unique features that has been observed in the ransomware landscape. The first shifts, and let's say it's the main evolution, it's in the encryption schemes these threats are using. The main shift has been observed. The fact that they are not using anymore RSA as an asymmetric encryption, but they are using elliptic curve Diffie-Hellman. What are the main difference is that with elliptic curve Diffie-Hellman, the private key that is used to encrypt the files are never stored on the disk, neither in encrypted form. And I will deepen this concept in the next slides very deeply. The second evolution is in the fact that all of the encryption implementation that has been implemented by ransomware are avoiding the usage of crypto API. The crypto API are the Windows function that are offered by operating system. And instead, ransomware developers, they are using open source libraries or custom implementation because these operations are much stealthier. This is the main motivation. And one interesting point that can be observed also from my findings is the fact that every analyzed families append a specific piece of information at each encrypted file. And this piece of information is needed for the decryptor to work. Okay, I am starting the talk with a little EV concept, but if you follow me, I think that you will find it interesting. And now I'm going to show what are the difference between the usage of RSA and the usage of elliptic curve Diffie-Hellman. I'm not a mathematician guy, okay? I'm not gonna use any formula, but please stay with me and you will see that's an interesting thing. Okay, whenever a ransomware, this is what happens in the ransomware that implements RSA as asymmetric encryption. When a ransomware wants to encrypt a file, like the secret TXT content, they perform data encryption. The data encryption they do is symmetric, because symmetric encryption is very fast compared to asymmetric encryption. So they feed the data input of the content of the file, and they feed as input key the symmetric key. And then the output is what? The encrypted buffer of the file, and is put inside the encrypted file, that is secret TXT encrypted. But the problem is how the ransomware operator are protecting the most crucial piece of information here, that is the symmetric key. And here is when it comes into the play the asymmetric encryption. So how they do it with RSA? The operator, what they do is they usually use builders to create their ransomware payload, their locker. So this is an offline operation they do. So whenever they have to compromise a company, they generate a couple of RSA public key, that is the public key and the private key. The public key is the one that is embedded in the ransomware executable, in the locker, and the private key is the one that is kept in secret to the attacker. When the ransomware payload is deployed to the infrastructure to disrupt the services, what it happens is that the payload generates a random buffer key that will be used as the symmetric key. Okay? And the next operation is to protect this piece of information. And how they do it? They use RSA. Okay? And in the RSA encryption, what they are providing as input parameters, they are providing, of course, the random key that must be encrypted, and the public key, that is the one that is embedded in the ransomware payload. And last but not least, the data output, that is the symmetric key encrypted, is appended to the end of the encrypted file. Okay? This is a very crucial operation, otherwise the ransomware couldn't recover anymore the file exactly. Then, of course, the ransomware destroys the key from the memory, and the only things that remains to decrypt this file are the encrypted symmetric key that is appended to the end of the file. How the inverse operation works? Basically, the decryptor of the threat actor will perform an RSA decryption of what? Providing the input key, the private key that was kept in secret, so he is the only one that holds this piece of information, and provide as an input what? The encrypted symmetric key. And as output, it has the symmetric key, and it can invert the operation and can restore the file. Okay? This is what has been happening in the last years of ransomware developments. Now, let's see what is the evolution with the elliptic curve Diffie-Hellman. It's a bit more convoluted, but it's more effective. Okay, this is what I was saying. Only this key can decrypt this piece of information and allow to decrypt the files. Okay, when elliptic curve diffie-Hellman, we have the same operation, the symmetric encryption. What it changes, it's the asymmetric encryption. And it's the one I'm showing at the bottom. So the operator now is using elliptic curve diffie-Hellman to indicate setup phase. So they are generating what? A couple of elliptic curve keys that are the public key, master key, and the private key, the master key. Then, of course, the public key is embedded in the ransomware payload, also in this example. Then the ransomware payload is deployed to the machine. And once the ransomware is executed on the machine, it's generating another couple of keys, okay? And these couple of keys that are ephemeral keys, so ephemeral means that are used for a single session, but in this case, the ransomware are not encrypting any session. Their session is the file, okay? And what they do is to generate the shared key using elliptic curve diffie-Hellman with the key agreement phase, in which they provide what? They provide the private key that has been generated on the system, and the public key that is embedded in the ransomware payload. In this way, the shared key, this is the shared secret that is generated by the elliptic curve diffie-Hellman key agreement, is hashed and is used as a symmetric key. Okay, it's the same goal of RSA, but it's a bit more convoluted. And in the end, what is appended to the end of the file? Instead of appending the encrypted private key, they append only the public key. This is much more better from a security perspective of the encryption protocol. And in the end, of course, the key to recover the symmetric key are destroyed from the memory. And what is left to restore the file is what I'm showing here. Okay? So how the decryption could occur with only this information remaining on the system. The ransomware, when the ransomware operator, when he develops his decryptor, is using another time elliptic curve diffie-Hellman key agreement, and it provides what? As an input, the private key that he kept secret on his server. And as a public key, it reads the key from the file footer, okay? And this way, the shared key that is computed is the same key that has been used for the encryption, okay? This is the black magic of elliptic curve, okay? This is a nice thing. And of course, the operation in this way can be inverted. What are the main difference between RSA and elliptic curve diffie-Hellman is that the symmetric key never touches the disk, because in RSA, that piece of information you can see in the file footer is the encrypted key with RSA. In this case, we have just a public key, or elliptic curve. And it provides stronger encryption scheme. Okay, going to the next trend that has been identified in my research is the automatic discovery of internal resources to target. So every ransomware bundle a way to perform an internal enumeration of the resources to encrypt. The common trend is to identify all of the local directories and the remote shares. This is it's almost normal for a ransomware doing this operation. Instead, there are some unique implementation that performs a more in-depth seek, like Black Matter and Conti. Black Matter, for example, uses LDAP to query the machine registered to the Active Directory and then try to infect the remote shares. Conti instead retrieves the network addresses from the local ARP table. So it's more a network propagation. Okay, I'm going very quickly. This is the reversed code of how Black Matter query the LDAP servers to get the computers to infest. So they are using IDS open object. They are connected to the LDAP root DSA context. Then they are querying the CN computers, and the returned value, it's a numerator that by just enumerating over this structure will give you back all the machine registered to the infrastructure. The third trends that has been observed is the fact that all of the identified ransomware put so much effort in the task parallelization of the data encryption. The main motivation around this is the fact that in this way the data encryption goes that fast that it shortens the time of reaction of the security team of the compromised infrastructure. All of the ransomware implementation prefer a native multi-threading approach instead of using multi-processes, because multi-processes it's quite noisier. And the main trends observed is the usage of I/O completion ports. That's an internal way that Windows allow you to manage the synchronization and the multitask operation. Instead, there are some unique implementation worth to mention. In Babuk, for example, Babuk, they do not use the I/O completion ports. Instead, they are using a custom implementation of the thread pools with the custom queue and shared data structure. And this has less overhead than using I/O completion ports. Instead, Black Matter uses undocumented Windows function to increase its process priority and its process I/O priority. And this what means is it means that the kernels, when the thread from the ransomware came, will prefer the scheduling of this thread instead of other threads of the system. And this grants a slightly improvement of the performance. Okay, I'm going very quickly, because otherwise I won't have time for the rest, but I will put the slides online. This is the reversed code of the undocumented function used by Black Matter. So they basically are using NT set information process with process IO priority and the process IO priority IG value. So it means that these threads, the threads in this process will be privileged compared to other threads of the system. The same goes to the priority class. Sorry, it was inverted. The IO priority class is for the file system, and the priority class is for the threads of the ransomware. And the value is priority class above normal. So as I told you, they are preferred these threads instead of other threads of the system. Last but not least, the trends that has been observed is the fact that the ransomware operator, they develop a series of functionalities to maximize the encryption damages. So what are the common trends? The common trends are the fact that they kill a set of processes and the services starting from unwanted names. Okay? So for example, they kill the SQL server's processes, they kill the Excel processes, all of the processes that can cause locking mechanism on the files to be encrypted. Moreover, for the unknown processes that are not known to the ransomware developer, they leverages the Restart Manager API functionalities. That's very interesting because it allows to get all of the processes that holds log conditions on the files to be encrypted. So the ransomware use these functionalities in order to retrieve the PID of processes and killing these processes. Another common feature is the fact that they always erase the volume backups. So the most common knowing as shadow copies. The methods that has been observed mainly are the usage of WSSadmin, that is a Windows utility, in order to delete the shadow copies or resize the shadow storage. So there are two different approaches. Or they use auto processes COM objects. So in this way, it's a more indirect way to delete shadow copies. And what they do is basically interacting with the VSS providers through the VMI services. Okay, this is the Babuk implementation. The Babuk has been leaked the source code. Okay, so for Babuk, I didn't need to reverse anything because there was source code. And this is how they implement the killing file lock holders functionalities. So they are basically using RM start session, that is the Restart Manager API functionalities. They register the resource in the Restart Manager by saying, okay, I want to see secret.txt, who is using it. And then RM get list give back all of the processes using that file. Okay? Then they open that process and kill the process. And then they encrypt the file. Very, very effective. Now, grouping all of my results, this is the key part of my research. Grouping all of the results extracted, I have been able to provide a behavioral characterization. So what it means is that starting from the 4 macro features, I have been able to identify sub-features that could be more meaningful. For example, for filing directories enumeration, how can be divided? Can be divided as this subset of operations. So mount hidden volumes, local drive enumeration, remote drive enumeration, and file enumeration. File encryption has been identified these operations. So asymmetric encryption, symmetric encryption, key randomization, encrypted block writing, and file footer writing. For the encryption optimization, kill unwanted services, kill unwanted processes, shadow copies deletion, kill file lock holders, increase process priority. And for the encryption parallelization, we have the multi-threading and the synchronization. Why I spelled each one? Because this is very important, because as a malware analyst, if you know what you should expect from ransomware, it easy your analysis, because you already know what you are going to look into. So as I told you, these 4 are the main features that I assume in the beginning in my threat model. And these sub-features are the interesting find that can be used as a generic characterization of the ransomware, at least for the data encryption stage. Of course, the main goal was not to provide knowledge to malware analysts, because malware analysts, most of them are already know this kind of operation. The main reason was to have a threat model that, by mapping the implementations, could allow to spot commonalities between implementation. The mapping that I'm going to show in the next slides has been based on the NT-Win32 API usage, and I'm using this kind of mapping because with the Win32 API usage, we can understand what are the side effects and the telemetry that is left on the system and can represent for us, defender, a behavioral detection or at least a detection opportunity. The goal of this mapping is to provide a way to recognize overlapping implementation across families, and this is the development of effective detection to identify ransomware behavior commonalities. Okay, I have this. It's a big Excel. Okay, I have put at the bottom the public spreadsheet with all the results. So maybe after the presentation you can consult it. But I want to present you the main results. These are the results for the file and directory enumeration micro features. So what we have in this table, we have in the first column the sub feature. So the behavioral characterization that I showed in the last slide. In the implementation are the Win32, they are the implementation. And the implementation has been based on the function used on the operating system. And the other columns are the analyzed families. So Babuk, Black Matter, Conti, and Revol. What we can observe here. These are the point of interest, because as you can see, the local drive enumeration and the file enumeration are using the same implementation. Okay, so if we identify this operation, we are sure we are identifying almost all of the ransomware families. These are the results for the file encryption. And an interesting observation of the file encryption, because the funny thing is that my research was based on the encryption, and I thought that I was going to find something interesting in the encryption, so the asymmetric encryption, the one you see in the left. But the problem, as now I can see, and you can see too, is that every ransomware is doing whatever they want. So this is not providing us any detection opportunities. And instead, these sub-features that allows to, they are helper features, but are still vital to write the encrypted content back to the file. They are some, let's say, vulnerabilities, because they use all of the same implementation. And in next slides, I will show you some behavioral detection based on this overlapping, on these commonalities. These instead are the results for the encryption optimization. And one of interest are the one on the right, the restart manager API usage, because it's used by every ransomware. And if you think about it, a ransomware can make a lot of damages without using restart manager API. But the goal of the ransomware, they are developers too. So they try to build their software as much better as they can. And this can be used by us, defender, to create detection around it. And this is the last category, the last feature, encryption parallelization, that has some commonalities in the multi-threading implementation. But for this kind of feature, I do not recommend to use it for detection opportunities, because this kind of implementation are hard to discern between banning usage and malicious usage. But, it's there. Okay, now it's the last chapter of this presentation, in which I'm going to give some recommendation on the behavioral detection that are based on the overlapping implementation, okay? Now things is going to be a little bit more technical, but I think that it's fun stuff. So if you follow me, you can find it very interesting. Consider that all of the behavioral detection that we will see now are based on the telemetry that usually an antivirus engine or an ADR engine can get. So it's very deep telemetry. I'm not expecting that a SOC analyst can use this as a behavioral detection, okay? So starting from the tables I showed before, these are the ones that are overlapping. So I'm going to present 4 different behavioral detection, one based on the file enumeration, one based in the key randomization, one based on the file footer writing, and one based on the kill file log holders. As you can see, the naming of the sub-features, it's quite self-explanatory, okay? Let's start with the first one, the file enumeration detection. What has been observed is that every ransomware performs the sub-feature file enumeration with a sequence of this API call, that is find first file X and find next file. In find first file X, the inputs we have are the drive, the directory, and then there is the wildcard character that allows to enumerate all of the directory on the system. And find next file is keeping the recursion going on. The usage of this particular function with this value, the wildcard, the char, generate a specific IRP at the kernel level. What is a IRP? For those who are not familiar, a IRP is a packet that contains all of the information describing an operation on the file system. So an IRP will contain operation, file creation, pad, like secret, length of the write, and so on and so on. And why we are interested in this kind of telemetry? Because kernel detection is what you are looking for usually. This is a screenshot from Procmon, and this is exactly the operation generated by this file enumeration by a ransomware. So what we have here, we have the operation directory control, and the file information class, file bot directory information, and the filter is a star, okay? So we can identify the file enumeration by just monitoring these kind of events. What is the problem with this approach is that it's not just only the ransomware that enumerate the file on the system or directories. Even backup software do it, okay? So we need a way to discern between the two behaviors. And here is where it comes into the play, the concept of cross-drive file enumeration. Because every ransomware, before doing the enumeration of all the folders, what they do is trying to reach as much resources as they can. So they try to mount remote shares, they try to lateral movements to other systems, and they are going to spread the file enumeration over all of these resources. And this is, of course, not something that does backup software, and it's more related, of course, to ransomware behavior. And the advantage of this kind of detection is that, as I told you before, the detection spot occurs at the kernel level. The kernel level is what we are looking for as a defender. Okay, this is I'm showing you process monitor capture because are very easy to compare to what you can develop in your AV engine. Okay, if you develop a mini filter driver, you can get the same result of Brockman. In this case, it's a Babuk execution. I have filtered out operation of directory control, and you can see that all of the directories are being enumerated by using the star wildcard. What is the anomaly here? The anomaly is that this kind of operation is dispatched to all of the drives: C drive, M drive, N drive, a shared drive like VMware Host. Even the recovery drive is getting encrypted. Okay, this is quite weird. The second detection is the file footer writing detection, and it's based on what I showed in the encryption, all of the graph about the encryption. So every ransomware append a piece of information, a very important piece of information at the end of every encrypted file. And this can be attacked and can be took as a detection opportunity. How they do it? With the same implementation, they use set file pointer X and they use the constant file end. So they are just telling the file pointer to go to the end of the file. And then they use the write file where they write the file footer struct that usually contains the private key and some other information. And then the size of the write is the size of the struct, okay? And also in this case, we can expect this generate a specific telemetry at the kernel level. So we have a IRP at the kernel level, but in this case, it's different between compared to the previous one. Now we have the write operation of the IRP. And instead, the parameters of the IRP, interesting, what are? The offset that points at the end of the file, and the 96 is actually the struct that contains the private key. So how we recognize this kind of append operation in an effective way? If we intercept this kind of write before a write occurs, okay, we can check the byte offset parameter, and if it is equal to the actual size of the file, most probably is an append operation. Then we get the length parameter, and this is the structure length. And in this way, we are, let's say, aggregating information about the structure that has been appended to the files. Unfortunately, this structure size is different between the ransomware implementation. Even if in a single execution we will get the same number, but maybe Babuk use 100 bytes, Black Matter could use 200. So we need a way to understand dynamically what is this size. And how we can do this, we can aggregate the number of appended operation. And then we will see in the next slide that with a dictionary data structure, we can understand what is the size. Okay, this is an example of Babuk encrypting a photo, some photos. Okay, you can see in the pad in the fifth column. And the first, for each file, there is two writes operation. The first write, what is? It's from offset 0 to offset 10,000. It's basically encrypting all the file. The next one is starting from the end of the file and is appending 96 bytes. And this is the kind of weird operation. At least weird if it's done to every file. Okay, so every file, there is an append operation from the end with 96 bytes. And this, of course, this is an example of only 3 files, but this occurs to every file of the system. So if we count this, how many file markers are appended to files, we are able to understand if a file footer writing is happening by a ransomware. How we can effectively, this is, for example, we can use a dictionary data structure to keep track of these writes, but this is just an example of an implementation. Everyone can use their own way, their own data structure, and so on and so on. And what we should observe is that once we have arranged our data by containing the key, the size of the structure, and as a value, the counter of how many appends occurred, when a ransomware is executed, we should observe that one key of this dictionary will have the counter that is exceeding a threshold, for example, 300. So it means that 300 files has been appended the file footer of the ransomware. And also in this way, the detection spot occurs at kernel level. And we usually, as defender, we like kernel detection. The third behavioral detection is Restart Manager API usage. So the Restart Manager API has the common implementation that are the first three API calls. And why the ransomware are using this kind of approach? Because whenever they try to encrypt a file, they call a create file function. And if this function fails, they assume, they say, okay, maybe I cannot encrypt this file because some other process is locking this file. So they use the restart manager the restart manager will tell, okay, PID2 is using, no, PID2 is impossible. PID10 is using this file, so they get this PID and they kill it. The problem with detection is that when we want to do detection, we try to achieve the lowest possible NT-API call. So RM start session that is from the restart manager DLL, it doesn't like. Usually we shouldn't like that kind of hooking on this call. So by reversing this DLL, we can see that the lowest level possible call is NT-query information file. Okay, so by monitoring NT-query information file with this undocumented file information class that has the longer name, file process D using file information, we can understand if a ransomware is using too much this functionality. And usually banning applications do not do it. And when we see a peak usage of this kind of functionality, we should probably raise some flag, some alert flag. The problem with this approach is that we need to monitor the NT-query information file from the userland. And userland level detection is something acceptable, but it's not like kernel detection. Last is encryption key randomization detection. Basically, every ransomware, in order to generate the private keys for the encryption, they use pseudo-random number generators. And this kind of, by the fact that the ransomware generates a unique private key for every ransomware, for every file to be encrypted, this generates a high volume usage of this random number generators function. What are the main functions that are used are crypt_gen_random and crypt_gen_key from ADWAP32. And the particular value provided as an input are, so crypt_gen_random generates just a random buffer. So you need to tell how many bytes of random buffer you want as an input. And usually ransomware use the input what? 16 or 32 bytes, because it's exactly the key sides of symmetric encryption. So AES is 32 bytes, AES could be also 16 bytes, so this is quite abnormal, at least if you do it a lot of times. Unfortunately, this kind of detection is not generic as the others, but it can still be used as an opportunistic way, because in Black Matter, for example, they are not using function by the operating system, but they are using a lower level approach. They are using assembly instruction. Conclusion. Giving insights of what are the core operations, characterize the data encryption stage, and make the analysis of this complex threats easier. What it means is that by knowing this kind of knowledge, when you are going to reverse a ransomware payload, you already know what you should expect. And when you already know how your threat is operating, it's much easier, your analysis. Identify the commonalities in implementation allow to create behavioral detection. And this behavioral detection are based on the telemetry that are side effects generated by the API code that I have showed you and has been tracked. And the main reason for preferring behavioral indicators over static indicators is because they are much more reliable and harder to evade. Think about if a ransomware wants to change their code to evade the file footer logic detection. You don't even know how many tests and how many costs they will get to evade that detection. And even the cross-drive file enumeration, if they want to evade to for example, enumerating remote shares, they are actually limiting their payload. So as a defender, this is what you are looking for. And all the TLDR of my research is that the behavioral detection is the right approach of scalable ransomware countermeasures. Some special thanks. Sentinel-One's team, Claudia, Daniel, Andreas. If you want to meet me and us, you can approach us later at the Sentinel-One stand. Idan and Chuang-Dong, that without their precious contribution, I couldn't make this research. And thank you for your attention.
All right, thank you, Antonio.
Yeah, please, if you have any questions, we have a big slots, I think, so.
Hello, thank you for your explanation. I'm not a technical guy, but I think I understood, so it's a good sign.
Thanks.
Actually, I have a thought about what you present is actually giving information to any ransomware group, how to change and how to improve their software. So what is, first perhaps from Sentinel-One, the approval of the board or whatever directors, or for the community of malware analysis? Is it from a moral perspective good to publish or to explain us this, that they will have the information? And perhaps as a second or following, how long will be your work or this work valid? In 3 months, they change the ransomware and then you can throw it away? Just,
Yeah, I will, smart question. The first thing, I think that security by obscurity, it's not something that we should be looking into. So if the AV market and the EDR market shouldn't work on security by obscurity, because this is a fundamental approach, in my opinion. The nice thing, what is that if everyone like me is publishing this, you don't even know how much the cost for developing their ransomware to evade is increasing. And what I'm telling you is that most probably everyone is ignoring most of this detection because they will start to understand that it costs a lot. Maybe it is developed by just Sentinel-One, and it's not the case. This is not still in the Sentinel-One agent. And so my message here is, if everyone is releasing detection, that of course detection is aimed to defenders and not to attackers. Of course, attackers will always have advantages. Even if you publish a POC of an exploit, attacker will have advantages. But for the detection, if everyone will do it, the ransomware development cost will increase a lot. And maybe we are seeing less costs, less ransomware attacks. Who knows? We don't know because we cannot measure this kind of information. Sorry, about the second question. Yeah, exactly. And this is the main reason of tracking the implementation, because if you track setting indicator like caches, one single char appended to the file, it's gone. And if you instead monitor for implementations, the system doesn't allow you to do the same thing in a different way. For example, if you want to move your pointer of a file to the end of the file, maybe there are 3 or 4 ways. And if you create this kind of detection that are based on the output of the code, yes, but the code must pass by that way, they are very effective and maybe they last 4 years. I expect that this kind of detection will last 4 years. And if this kind of detection, if that was released 3 years ago, they were working. Okay?
Hello, thanks for the talk. I think it was interesting because for me, analyzing ransomware was something I did at nights just to have fun. And you talk about dynamic detection using Windows driver mini filters, but how about using the static analysis for detecting ransomware? Because you talked about the common APIs for example, cryptography. But you also said that right now there are some ransomwares that use Intel instructions for applying cryptography, or even if you use a static compilation of some APIs, you will have the code without any symbol.
Yeah, the problem with static indicators and static detection in general is the fact that, for example, all of these API is not imported statically. So if you write a URL to detect these imports, they are failed because they use dynamic resolve. My research was not to unpacking ransomware because all of these ransomware were packed and there was a lot of operation to unpack it. So by relying on behavioral detection, you are getting rid of packing and unpacking. And it's the worst problem we have in detection because someone using sandbox, but sandbox, in my opinion, are bad to analyze behaviors. And there are other approaches like kernel detection or userland detection. And in this way, you are sure that if the attacker buy another packer, your static rule is gone. With behavioral detection, no. They have to change. They have to hire the developer and say, I need that this behavior change from this and to that. And we know how we developers we are. If someone come and say, you don't do this in this way, but you have to do it another way, it requires more effort. Okay? This is I think that all of these detection are not bulletproof. The goal of detection is to increase the cost of the attacks. This is the most thing that you can do. Welcome.
Yeah, I have another question here.
Sure.
First of all, thanks for the nice talk, very interesting. And this is probably in the same line that you have said right now, that you said that this is not bulletproof. Well, for the detection of the writing of the footer on all of the files, well, it's clear that it's being done for all of the files, and this is suspicious, to say the least. But for the enumeration of the processes that are holding logs on files, this is perhaps some common API that it's used by, I don't know, Process Explorer maybe to see what are the open files by some specific process or whatever. So what are the thresholds that you use to detect or to tell apart legitimate calls to this API or suspicious accesses?
Yeah. So these detection are like results that can be took by detection engineering team and can be implemented. The process involving a development and a deployment of a detection, behavioral detection, requires what we are saying. So, okay, this is a detection. How many false positive it has? It's not something that was in scope of my research. This is how much false positive it has. If we use these kind of thresholds, we are reducing false positive by X. If we are using these other thresholds, we are improving efficiency, because detection costs also efficiency of the system. So all of these kind of results can be, it's always a trade-off, of course, but this kind of result and adjustments to discern false positive is something that is done in the development of the detection engineering. That's not something covered in my research. It was more of a threat intelligence research, Maybe it's a challenge that when detection team are going to implement this, we'll have some challenges like this. Thank you.
Hello, hi.
Hello.
Nice talk. So the question goes a little bit along the lines of what my colleague said, and is like, when you filter IRPs in the kernel, I mean, you have thousands and thousands of IRPs. So how do you actually discern? Because then you lose the context on the user space when you are in kernel. So how do you actually understand the ones that are actually malicious?
Usually the kernel, when you get the IRP from the kernel, you have also the process ID that they are doing process, and also thread ID you get. And what you need to be, but this is more a problem of your AV engine that you are going to develop. It's more about what if a ransomware is forking 3 processes. Injecting another process, it's something you detect separately, okay? But what I wanted to say is that if you looking into IRPs and you keep tracks of the context, like for example, PID1, PID PID5, PID6, PID7 as a child-parent relationship, and you know that this is all ransomware, you are monitoring the IRP for these three processes. But this is something that should be cared by your engine, by your infrastructure. It should not be dependent by detection. Detection should be generic as possible. Yeah, but the threshold. You are going to detect file footer detection stuff.
Yeah, but for example, log files in the system will affect everything. A log file.
No, but the file footer appending are a specific value and are done to the whole file on the system.
Yeah, I understand, but you can have false positive as much as you want. I mean, a size of 96 is an arbitrary size, so
This kind.
you may have multiple of these.
Mhm.
And when you go through the kernel, the problem is that it may get too generic. Like
Mhm.
your objective may get too wide, you know. So I understand that maybe it works really well for this technique, but generalizing it goes into the space of, hey, maybe here I'm detecting everything.
Maybe I misexplained the generalization. Generalization is for the implementation. Okay, you don't do everything with the IRP and the kernel. You do it where you can. For example, to intercept in the write operation, it's something that every antivirus do. You need just only to add another check to do this kind of checks. As I said also to the other guy, it's the false positive measurements. We can argue about that for all the day, but in the end of the day, it regards measurement. And this is something that I haven't done, but what I can say from my empirical experience, this should require very little adjustment, at least for the one that I have presented today.
I think we have time for one last question. Who's over here?
Thanks for the talk. I was wondering, maybe a more general question about ransomware. Have you ever encountered like encryption or obfuscation efforts in the ransomware code or behavior, like noise introduction in the key append to the footer for the size detection? Or is it like pure performance oriented because of the cost of the malware development?
Sorry, you mean if every ransomware is appending the file footer at every file?
No, I was wondering if ransomware developers are making any efforts in hiding this behavior, in obfuscating the code or their behavior to evade, or are they just pure performance oriented?
Yeah, the nice things about this detection is that as long as you hide and obfuscate your code statically, the operation would be the same. Or if you change the code, the source code, and you are saying, okay, the file enumeration, I'm not doing this, and I'm doing it this way, in this other way, but I challenge you to find another way to use that two API call. If they use, everyone using this approach, maybe they are not the only approach, but they are very few, okay? So the advantage of having behavioral detection is that it doesn't matter how much money the ransomware pay for the crypter, for the packer, for the static obfuscation. This works everything. If you take Babook or Black Matter and you pack it with the Temida, Armadillo, with Crypto One, you will get the same events. The only way to change that telemetry is to change the logic of the code. So the ransomware has to do an investment, the ransomware crew, to make their developer changing their code habits, making more research, it's...
Yeah, that was exactly my question. Like, are they making this effort today? Do you see that like in the wild, in the different ransomware?
Yeah, they are exactly, the ransomware crew are organized very well. The rival organization, for example, had 10 developers just developing the locker, the one that I analyzed. Then they have the penetration tester that are internal, so the one that get an initial access and perform lateral movement and privilege escalation. Then they have the initial access program. They are well organized, and
okay.
Of course they are all paid. Okay.
Thank you.
All right, let's have another round of applause for Antonio.
Thank you.